All right, so we're going to talk about waves and we're going to talk about sound today. So we have sine waves, right, start at the origin, and cosine waves start at the peak. And so we can discuss something called the wavelength of the wave. And this is just the distance over which a wave's shape repeats. So what I'm showing you here is one wavelength of a sine wave and one wavelength of a cosine wave. So our cosine wave is going to go from the middle of a peak all the way back to the middle of the peak. Our sine wave, one wavelength, is going to include an up and a down, right? So right before it starts to repeat. So each of these is one wavelength of a sine or a cosine wave. So we can label aspects of this wave. So the first thing we're going to want to label is going to be the amplitude. And remember that our amplitude is going to be our maximum displacement. Well, we can have maximum displacement in the positive direction and maximum displacement in the negative direction. So going from equilibrium to maximum displacement in the positive direction, I have my amplitude here on the wave labeled, and it's 2. And same thing here. My amplitude in the negative direction. So something you'll have to do on the exam is label parts of a wave like the amplitude of the wave. We can also label the wavelength, right? So my wavelength here is unfortunately like 6.125. Yeah, give or take 6.25. It's not an even number. I should have made it an even number, but I didn't. So our wavelength here. Same thing with the cosine wave. It is going to be from equilibrium to the peak. So these are the amplitudes of my cosine wave and my wavelength of this cosine wave. So what's interesting is that our wavelength and our frequency are inversely proportional. If these waves are traveling at the same speed, the one that has a higher frequency has a shorter or a smaller wavelength on top, and the one that has a smaller frequency has a longer wavelength to it. So, what exactly is a wave? Well, specifically right now, what we're talking about are mechanical waves. So, like a light wave is different, has different properties to it, but a mechanical wave requires a source of disturbance, it requires a medium, and it requires either a physical connection or some sort of mechanism. So all waves carry energy and they carry momentum, but the amount of energy that's transmitted through the medium and the mechanism responsible is different in each case. So here we have a pulse or a traveling wave, right? I have the wave traveling down this string, for example, but my string itself is not traveling. My medium in this case is the string. The source of disturbance is me flipping the string up and down. And the physical connection is the fact that this is one continuous string. So this would be a traveling wave. We also have something called a transverse wave. And this is where our medium, and our medium in this case is a bunch of particles, our medium moves perpendicular to the direction of the wave. So my medium is moving up and down. Like if we look at one little particle, it's moving up and down in the y direction, but my wave is traveling in the x direction. If I follow the peak of this wave, it's traveling in the x direction. So this is a transverse wave. The medium and the direction of the wave are perpendicular to each other. A longitudinal wave, the medium and the direction of the wave are parallel to each other. So if we just watch one of these particles, it's going to be oscillating back and forth in the x direction. My wave is this area of compression labeled that is traveling in the x direction. And I think what's really interesting to note is that the particles are not traveling the distance of the wave. The particles are just oscillating back and forth in place. This wave is propagating through this medium. So when two waves are in the same space, they can interfere with each other. Whenever we think about like objects, objects don't really interfere with each other. To my cat's surprise, me and my cat cannot share the exact same space on the pillow at the same time. This is a little bit different for waves. So with waves, two waves, or honestly, dozens of waves, can share the same space at the same time. And so what we're seeing here is a combination of something called constructive and destructive interference. So when the amplitudes in the positive direction line up, right, and the waves kind of look like lasagna, perfectly stacked on top of each other, we get constructive interference. And when they're opposite and it kind of looks like egg cartons, we are getting destructive interference. So, I don't know if I'm going to be able to actually pause it. It's okay, I have more examples. When both waves are traveling, obviously we get a new frequency, a new oscillation that is occurring. So, sound is what we're really interested in right now. So sound waves are those longitudinal waves, right? Sound waves are these longitudinal waves, and they're just pressure waves moving through a medium. So whenever we're thinking about sound waves, generally we think about air, but it doesn't have to be air. Like if you scream into your pillow, people still hear you. The medium is the pillow. Anybody that has ever lived in an apartment knows that sound waves absolutely travel through walls, and walls are a medium, right? It's drywall, it's gypsum. So, sound waves are specifically longitudinal or pressure waves that travel through some medium. And so, vibration of sound disturbs the air, and it causes this pressure wave to propagate through. So, whenever we have areas of high density, these are called compressions, and areas of low density are called rarefactions. And so we can actually draw out this sine wave here, where areas of high density, these compressions, result in a positive amplitude, and the rarefactions are a negative amplitude, and it ends up being a sine wave. So these peaks and valleys are generally called crests and troughs. And so the motion of elements in the medium, right, in the medium of air, it would be the molecules in the air. In water, it would be like water molecules. So, anywho, the motion of the elements in a longitudinal sound wave, these elements move back and forth, right, along the direction in which the wave travels. Right? So we have these areas of compression and refraction, and what we're actually getting is like an oscillating motion back and forth, a changing pressure, so they oscillate and they move, and it allows the sound wave to propagate through the air without the air actually moving. So it's the collisions of these particles that are causing this sound wave to propagate through from one place to another. Meaning that if you were in a vacuum and if a tree falls in a forest and the forest is a vacuum, the tree would not make a sound because there were no air particles in the vacuum to propagate the sound wave. So there are a bunch of different types of longitudinal sound waves, right? Whenever I talk about sound wave, most people just think audible sound waves. But these are a very small fraction of sound waves. So audible sound waves are just the sound waves that are sensitive to, like, the human ear has sensitivity to. You also have infrasonic, right? So an earthquake wave is technically a sound wave, and it is infrasonic, but then we also have ultrasonic waves, which are above our range. So like that dog whistle is generally in the ultrasonic range. The dog can hear it, we can't. It is still a sound wave. So this is also used by like bats and dolphins for echolocation, but it can also be used for imaging, right? Ultrasonic waves, ultrasound imaging. Sound travels through human tissue. Reflection of the sound waves from different tissues can be used to create an image. So the wave speed is just how quickly a wave moves through a medium. So v is going to be our wave speed. and it is equal to either the wavelength divided by the period, or more frequently you'll see wave speed equal to frequency times wavelength. So, these purple slides I pulled from my conceptual physics class, just because I think they have really good graphics. So, yeah. So wave speed is just how fast it moves from one location to the next location. So I have two waves here, and they're moving at the same velocity. They're moving at the same wave speed. The difference, though, is that one has a very short wavelength. The one on the right has a very short wavelength, so it has a higher frequency. The one on the left has a longer wavelength, so it has a lower frequency. A wave's speed isn't set by the source of the wave. It's set by what the wave is traveling through. So I can send the exact same wave into air, water, and steel, and they're all going to have a different wave speed because it's dictated by the property of the material, not the wave itself. So sound moves faster through water and bone and steel than it does through air. And if we look at our top little jiffy here, it has a lot to do, or you can look at the little dominoes one, with how closely the particles are packed together, how quickly they can transport energy from one particle to another, right? So if we change the material, we change the speed of the wave. If I send an ultrasound into your body and it goes through skin and your fascia into muscle and bone, each time it hits a new material, it's going to change the speed of that wave. Same material, same speed, no matter how the wave was made. It is all going to travel through that material at the same rate. So, frequency and wavelength trade off, right? The speed is determined by the medium, so frequency and wavelength can't both go up. They trade, right? So if we pack more wiggles into each second, we get a higher frequency, and each wiggle has to be shorter, right? So our little kangaroo on the top. If we have fewer wiggles per second, or a lower frequency, that means we have to have longer stretched out waves. We never get both. If we raise one, the other one is going to drop. So we can calculate the speed of waves on a string by looking at the tension on the string and the linear density of the string. And we can also calculate the speed of sound in air, right? So for sound traveling through air, it is temperature dependent because we need to understand the rate at which the particles in the air can carry the energy. But for the most part, for this class, we're going to assume that everything is room temperature, so the speed of sound in air is always going to be 343 meters per second. So, let's say that we have a sound wave, and we want to figure out the intensity of this sound wave, right? So we want to figure out something called the decibel level of this sound wave. So, we do have a threshold of hearing, right? And that is 1 times 10 to the negative 12 watts per meter squared. We also have a threshold of pain. So you can produce sound that produces physical pain. And that is 1 watt per meter. Google it. So we can calculate the decibel level as 10 times the log of the intensity of the sound divided by the threshold of hearing. And our threshold of hearing is provided here. So what's interesting is that if an object is producing sound, it is generally propagating out as a spherical wave. And so we can calculate the average, the intensity or the average power per unit of area as this propagates out. So as my sound wave propagates further and further away, as my radius increases, my intensity is going to change, right? If you're sitting close to me, I am very loud. If you are across the house, I'm probably still loud, but not as loud. The intensity, and thus the decibel level, is much smaller. So whenever we have sound that is produced and we incorporate a little bit of motion, we get the Doppler effect. So we see this all the time whenever like a fire truck drives by and it sounds like the pitch has changed in the sound that's produced by this fire truck. So why does this occur? So, right, sound propagates out as circular waves, and we can imagine this from my conceptual physics class as an object bobbing up and down in the water, and like the waves propagate out in the circle. The object isn't going anywhere, but the waves are moving away from this object, and they all have the same frequency, and that frequency is the same as the object that is bobbing. So what if my object starts to move, right? What if my fire truck starts to move past me? Well, when this occurs, all the waves start to pile up in front of the object and spread out behind the object. And so we get a perceived shift in frequency of the sound of the object, right? So this is our Doppler effect. For a stationary source, an object that is not moving, all of the wave fronts are moving out with the same wavelength, the same frequency, right? Because it's all happening at the same speed. Whenever this object starts to move, the waves approaching an observer, so let's say that I have a person sitting in front, like this object is moving towards me, and I am on the right of it, the objects or the waves approaching the observer, I am the observer sitting in front of this guy on the right, are compressed, and I perceive that there is an increased frequency. The waves behind this object, if I am observing from behind the object, are stretched out, and it decreases the frequency that is perceived by the observer. So, this is a great example. The waves produced by the object are not changing frequency, but the frequency of wave that is encountered by a second object, either observer in front or an observer behind, they will observe a changed frequency, right? Because the stationary observer in front of this car has a higher frequency wave, whereas the stationary observer behind has a lower frequency wave. So, I think this is funny with the little eyeball. An observer in front would measure an increased frequency because they are experiencing a shorter distance between successive wave fronts. The person behind would measure a decreased frequency because they are experiencing a longer distance between the successive wave fronts. So, this is actually related to how ultrasound works, right? So, an ultrasound transducer emits high-frequency sound waves into the body, right? These waves interact with a moving target, like blood cells, and are reflected back to my transducer. So, the frequency of reflected wave changes depending on the motion of the target. So, for example, depending on the motion of blood cells within blood vessels. So, if the target moves towards the transducer, the reflected frequency waves shift increases. We get a positive Doppler shift. And if the target is moving away, then we get a negative Doppler shift. So what's happening here? Well, when a wave reaches the tissue, three things are kind of happening all at the same time. Some of it gets reflected and like bounces off and produces an echo. Some of it passes through to go deeper into the body, which is what you want. And some of it gets absorbed and turned into heat, but like negligible. You don't really notice it. So a small mismatch is really good because it lets most of the wave pass through, right? That's really good for imaging. We want more of this ultrasound sound wave to go into the body. If we have a huge mismatch, then, which would be something like tissue and air have very different speeds for sound moving through them, or like tissue to bone, then this causes most of that ultrasound to be reflected, so almost nothing goes into the body, and everything becomes shadowed. So that's why they use like gel on ultrasound. It removes that thin air gap layer between the probe and the skin so that they can get more of the ultrasound into the actual body. Fun fact. So, from that, they can take that signal and turn it into an image, right? And the machine maps echoes to pixels, right? So brightness would be echo amplitude, and depth would be like time delay, how long it takes for the ultrasound or the ultrasonic sound wave to go in, hit something, and come back. And so this can be color coded as well. So if something is flowing towards the probe, it would be red, and something blue would be flowing away from this probe. And if you do multiple poses, you can get like 3D images. So how do we calculate this? With this very fun equation that I definitely will explain more in person. Give it a look over real quick. But we'll definitely talk about this most of the class period.